Digital signal processing relies heavily on filters that can isolate or remove frequencies with surgical precision. Infinite impulse response, or IIR filters, are the high performance athletes of the DSP world. Today, we're diving into how we design these systems, moving from classic analog theories to stable, efficient digital implementations. Why choose IIR over the simpler FIR filters? It comes down to efficiency. Because IIR filters use feedback, meaning the output depends on previous outputs, they can achieve incredibly steep roll-offs with a much lower order or computational cost than FIR filters. This makes them ideal for systems with limited processing power, though it introduces the risk of instability if not handled correctly. Most IIR designs begin as analog prototypes. We choose an approximation method based on our needs. The Butterworth filter is the cleanest, providing a maximally flat response in the passband with no ripples. If you need a sharper cut, you look to Chebyshev filters. These trade off ripples in either the passband or stopband to give you a much narrower transition region for the same mathematical complexity. To convert these analog designs to digital, we have two primary paths. The impulse invariance method preserves the shape of the impulse response, making it great for simple low-pass filters, but it suffers from aliasing, where high frequencies fold back into the signal. The bilinear transformation is the industry standard. It maps the entire analog range onto the digital unit circle, avoiding aliasing entirely, though it introduces a nonlinear warping of the frequency axis. This warping effect is defined by the tangent relationship between analog and digital frequencies. Before we design the filter, we must pre-warp our targets so the final digital result lands exactly where we want it. We also calculate the filter order n, which determines how many feedback loops we need. As you see in the formula, n depends on our required attenuation and how narrow we need that transition band to be. Stability is everything in IIR design. In the analog S-plane, a filter is stable if all its poles are on the left. The bilinear transform is powerful because it's a one-to-one mapping that squeezes that entire infinite left half plane into the finite area inside the digital unit circle. If a pole lands inside the circle, the filter is stable. If it drifts out, the system will oscillate out of control. In practice, IIR filters are implemented by carefully placing poles and zeros. A zero close to the unit circle creates a notch or attenuation at that frequency, while a pole creates a peak. To keep things stable and minimize noise from rounding errors, we often break high-order filters into second-order sections or biquads. This ensures that small errors in the coefficients don't lead to a total system failure. IIR filter design is a balance of efficiency, precision, and stability. By leveraging analog prototypes and mastering transformations like the bilinear method, you can build professional-grade filters for any application. Thanks for watching, and keep filtering.